Prithvi, hi, you there?
Yeah, hi Bhavya.
Good
Hello
morning.
all. Good morning.
Manjunath, you there? Uh, Manjunath, can you hear me? A quick audio check.
Yes, ma'am, I can hear you. Can you hear me, ma'am?
Yes, yes. Over to you, Manjunath. We'll start in 1 minute.
Yeah, okay, ma'am.
You want to sort out.
Manjunath, I think we are good to go.
Yeah. Okay. Good morning.
You're not audible, Manjunath.
Yeah. Can you hear me?
No, you're not audible.
Actually, it's audible to me. I don't know about others.
Can you check now?
Yeah. Can you hear me?
Yes. Yeah.
Okay. Yeah. Good morning, a warm and enthusiastic welcome to everyone. Everyone joining us today from across the nation for this high impact and technical webinar on FPGA. Brought to you by HAW Empowering Engineers. It's absolute honor to host such an event where the diverse gathering of aspiring engineers, educators, researchers, and industry professionals who share a common goal to explore and master advanced technologies in shaping of future in electronics. At HAW, we believe learning by doing. Since our inspection in 2020, we have been the forefront skill-based and industry-aligned training across the core engineering disciplines like electrical, electronics, mechanical, and civil engineering, and others. With over 1 lakh students trained, we take pride in our mission to bridge the gap between theoretical academics and real-time industrial requirements. Through a blend of practical sessions along with the project-based learning, internships, and corporate tie-ups and hands-on workshop, we equip the next generation of engineers with the right mindset and skill set to become the industry. Today's webinar is part of our continuous efforts to empower the students and professionals with the cutting edge technologies in field programmable gate arrays, a technology which is revolutionizing the digital world. So for this session, I want to invite or now let us take the lead through the power packed session where uh, the session will be led by the esteemed expert, Mr. Prithviraj Garu, senior DV engineer. So coming to Mr. Prithviraj Garu, he holds a master degrees in VLSI from NIT Delhi and currently serves as a design verification engineer. In his role, he is responsible for the FPGA verification for Intel Penga, Malaysia. Over the course of his career, he worked hard with the leading clients, including Intel, AMD, NXP, Semiconductor, Starfy, and Sequence. Additionally, he has published the papers in IEEE conferences. He brings the deep expertise in subsystem and SOC verification with the focus of developing semi-verilog and universal verification model methodology UVM test benches from the scratch. His core responsibilities involved in drafting test plans, documenting test scenarios, and creating SV and UVM based verification environments for the various SOCs and subsystem designs. He adapt the integration verification IPS, where we can call it as VIPs, and working with the protocols such as PCIe, JT, AG, Ethernet, and AMBA. Notably, he has contributed the two projects that advance to the tape out stage. Mr. Prithvi has the strong passion of design verification and process hands-on experience with the PCIe, both subsystems and SOC levels, where he manages power state transition and ensuring seamless movements between the power states and conducting coverage analysis at the full chip level. Now, I'm happy to invite Mr. Prithviraj, and I also happy to invite all the people, all the participants who have joined for this webinar with the passion, curiosity, and with one purpose. So now let me happily hand over this session to Prithviraj.
Yeah, thanks, Manjunath. Thanks for that brief info. Hello, guys. How are you all doing today? Hope you're all doing well. So let me start with the session. Hope I'm audible to everyone, right? Okay, so let me quickly share the.
Yeah, we can hear you.
Yeah, okay. Is the screen visible to you all?
Yes.
Okay. Thanks, Manjunath. Thanks for that brief info. So as Manjunath said, myself, Bijula Prithviraj, I hold master's degree from NIT Delhi. And
Sorry, Prithvi, sorry to interrupt. Can you please make it into an presentation mode?
yeah, sure, definitely. Yeah. So I have started my career at ST Microelectronics, which is a product-based company, as an intern, where I have worked on I3C, which is a cutting-edge technology at that time. As an intern, I have started my career, and just after that, I was working with many clients, as like Manjunath told just before. Currently, I am working for this client HDAI. It's a AI-based startup. So I'm working for this ETC HDAI. So that's about me in brief. So let us get a deep dive into the FPGA. Okay. I'm sorry, but not able to change the slide. Okay. So today's session is about FPGA programming, right? So let us see what is FPGA and what are the concepts involved in it and all those things. So this is the course contents that we are going to cover today, like what is ASIC, what is FPGA, and a brief introduction to both ASIC as well as FPGA. Okay, and what are the VLSI design styles, and basically what is the difference between an ASIC and FPGA, and then we'll focus more onto FPGA, like what is FPGA, why FPGA, how does an FPGA looks like, what is the architecture involved in that FPGA, and what are the features of the FPGA, why should I use FPGA, where can I use FPGA, and where can I use ASIC? Can't I use ASIC in a place of FPGA? Can't I use FPGA in a place of ASIC? So all such things we'll be covering today in about 1 to 1.5 hour session today. Okay. So let us quickly see like what is an ASIC? Can anyone give any example on ASIC? As you know, any random example? Can you you can what chart through the chart window? Can you give any one example about the ASIC? Anyone example on ASIC? Anyone example? It's okay, no problem. See, basically, all our processors within our mobile phone are ASIC based processors. And they are application specific processors. Okay. If at any point of time you feel like you are not following, please feel free to interrupt me through the chat window. And also, there my team is there who will be working in the background to take care of your doubts. Okay. So feel free to ask. Yeah, so let us see what is ASIC. ASIC stands for Application Specific Integrated Circuit. So what all the chips that we see in the market today, whether it is AMD Ryzen or i7, i6, i4 or the iOS processors, whatever the processor it is, all of them are what? All of them are ASIC processors. For example, in your laptop, you might be having a i7 processor with the 12th generation or 13th generation or whatsoever. So what is this? This is a i7 processor which can only be used for your laptop, which can only be used in laptops but not anywhere else. I cannot bring this and place it into my mobile phone and ask it to work. It will not work because it is tailored for to perform a specific function within your laptop. So it cannot do anything that you want it to do. It is designed specifically for a particular application, that is your laptop. So it can take any task that you give in your laptop, but it cannot work within your mobile phone. So ASICs are what? They are custom designed integrated circuits created for specific application or one specific task. So they are tailored to perform specific functionality, which can result in high efficiency and optimal performance. Okay, and so if at all you want to manufacture an ASIC, okay, application specific integrated circuit you want to manufacture. So there are some complex processors involved in it. Okay, which probably be indicate starting from the design specifications to the fabrication layout, which is basically at the transistor level. So it is quite difficult to achieve. On the other hand, let us see what is FPGA. FPGA stands for Field Programmable Gate Array. Field Programmable Gate Array means that it is programmable. See, the device itself is programmable. You can program it as per your needs. The name itself is telling you can program it. Okay, so if you see ASIC is what? It is application specific. If at all you have designed it once for a mobile phone, for example, in your mobile phone you might be having a Snapdragon processor, so it can only be used in your mobile phone. You cannot bring it out and place it in your laptop and ask it to work. It does not happen that way. So it is tailored to perform specific functions or specific tasks. On the other hand, FPGA is a programmable thing. You can program it the way you want, so it is not application specific. It is not application specific. You can program it the way you want. For example, today you want it to work as an AND gate, a chip that can simulate AND gate, so it will work as an AND gate. Then tomorrow you want it to work as an XOR gate, so it will work as an XOR gate. Or you have done some complex computation, and you want to perform operations that you perform on a scientific calculator, so your FPGA can do that. Okay, so FPGAs, on the other hand, are the semiconductor devices that can be configured by user. Okay, that can be configured by user. For example, the end user can configure this FPGA. So he can make sure that it will work in the way he want. But can you configure the ASIC? For example, you have taken, you open your laptop, you take your processor out of it. Can you configure your processor? I want to say, can you change? Can you do any changes to your processor? Is that possible? No. But on the contrary to that, if it is an FPGA, you can do that. You can configure your FPGA in the way you want. Okay. But the thing is, it is after the manufacturing. Once the FPGA is manufactured, then you can program your FPGA. But once your i7 processor is manufactured, can you do any changes to it? No, that is not possible. Okay, so that is where FPGA plays a crucial role, and the FPGA consists of matrix of programmable logic blocks. Okay, and also the programmable interconnects. Okay, this flexibility allows FPGAs to be reprogrammed. Okay, FPGA can be reprogrammed for various tasks and making them versatile. Okay, but these are potentially less optimized. I will tell you why it is essentially less optimized. There is a reason behind why it is less optimized for specific functions. So see here, in ASIC, reprogramming is not possible. Once the manufacturer manufactures this, then that's it. You cannot do any more changes. But here it is reprogrammable. Even after the device gets manufactured, what you can do is you can reprogram it. Reprogramming is allowed in case of FPGAs. Okay. So let us see the differences between ASIC and FPGA. Okay, so ASIC stands for application specific integrated circuits, whereas FPGA stands for field programmable gate array. So if it is ASIC is quite complex. See, if at all you want to make a chip, okay, you want to design a chip. So is designing a chip so easy? If it is so easy, why doesn't India have a chip manufacturing unit? Right, a basic question. So if at all you want to bring a chip out of it, it's quite difficult. Okay, designed all the way from behavioral description to the physical layout, you have to go through enormous number of steps. Okay, but on the contrary to that, if it is FPGA, in FPGA no physical layout design is required. The only thing that you need is a bit stream. Okay, you just need to make sure that you have generated a bit stream. With this bit stream, you can configure your FPGA. Okay, you can configure your FPGA. Today you want your FPGA to work as an AND gate, so it will work. Tomorrow you want your FPGA to work as a calculator, tomorrow it will work. So means today you have made it to work as an AND gate, tomorrow you made it to work as a calculator, means you are reprogramming it. Okay, it's just simply a programming. Okay, and here design must be sent for expensive design must be sent for expensive, and also it's a time consuming fabrication technology. I mean, like, if at all you want to bring a chip out of it, what happens is the time to market is minimum of 2 years. Okay, time to market for a chip in ASIC is minimum of 2 years. If it is FPGA, you can directly go to any vendor, you can buy the FPGA directly. For example, Arctic 7. Arctic 7 is a FPGA kit. You can directly order it in Amazon. The FPGA will be delivered to your home. You can readily open it and you can program it in the way you want within 2 hours also. For example, you want it to work as an AND gate. You can do this within 2 hours, so that you have a chip in your hands which can work as a FPGA. But for the same thing, for example, you want a chip which can mimic the behavior of a simple AND gate. Okay, you want a chip which can mimic the behavior of a simple AND gate. Even for this, in ASIC, what happens? The time to market is 2 years, because here there are lot of things, enormous number of steps that ASIC has to undergo. But if it is FPGA, nothing, just buy an Arctic 7 or any one FPGA. You just need to do a little process, then generate a bit stream, then that's it. You are able to make your FPGA work as a AND gate. You're able to see your FPGA as a AND gate. It means that you have simply generated a chip. You have simply created a chip which can work as an AND gate. But if it is ASIC, and if at all it has to work as a AND gate chip, what is the time to market? It is 2 years. But here it is simply 2 hours. So that is the advantage of FPGA. And also the money involved in bringing an ASIC into the real-time market is millions of dollars. Okay, if at all, for example, assume that you have a beautiful concept in your mind and you want to bring a chip out of it. Okay, maybe you have some concept. Okay, maybe you all know the scientific calculator, right? Okay, scientific calculator is there. What you want to do is you want to do some enhanced operations over it, which can do some Gaussian noise calculations and which can even do the computations of a 5 by 5 matrix, or which can even calculate probability or random variables, lot other things you want to include into that calculator. You know how to do that. So your aim is you want to bring a chip out of it. You have everything ready, and if at all you want that and you gave it to the implementation of ASIC, the thing it requires is 2 years of time. And the other thing is you should have millions of USDs, millions of US dollars are required. So it is quite complex and quite costly. On the other hand, FPGA, you can buy an FPGA kit at a price of 25K, and you do your own programming. You work hard for 2 months. Okay, you work hard for 2 months, then you will be able to see a product out. Means whatever the thought that you have in your mind, you're able to bring it out to the market in form of FPGA. Okay, it means that the thought in your mind is now converted into a physical thing, which can mimic the behavior of a chip, At the advantage that it is at a lesser price and lesser time. So if these are the advantages, then what are the disadvantages? Let us see. Let us see them over a period of time. So can you guess like what could be the disadvantages? Hmm? What could be the disadvantages? I'll tell you. See, if it is FPGA, FPGA can be reconfigurable. Today, you made it to work as a scientific calculator. Tomorrow, you want to make sure that it is works as a DSP processor. You can make sure that it works as a DSP processor. And the day after tomorrow, you want to work it as a something like a Chebyshev filter or Butterworth filter or some filter, some random filter. You want to make sure that it is working as. Then you can reconfigure it. But in ASIC, it is not like that. Today, you made one processor which works for DSP process, means throughout its life it should be used for DSP only, not for anything else. So it's a fixed circuitry throughout its lifespan, and it can be FPGA can be purchased off the shelf. It means that the time to market is quite less, but here it can only be designed as a custom or tailored to your needs. It is specific to the particular application. But what are the disadvantages of FPGA? FPGA size of an FPGA is, for example, size if at all size of a FPGA is this much. You might have seen FPGA ports. In comparison with this FPGA, size of a chip is this much only. Okay, you might see your processor in your laptop. How much is the size of your processor? Hardly this much size. Hardly this much size. But if it is FPGA, FPGA is quite bulkier. As it is bulkier and it has lot of components into it, so what happens is the amount of power that FPGA consumes is quite huge, whereas a ASIC, there is a very lower power consumption, and your ASIC will operate at quite higher frequencies, but there are some bottlenecks, or it is quite difficult for us to attain the high frequency rates if it is FPGA. Okay, and as I told you, in case of FPGA, time to market is quite less, and thing is high per unit cost. Because see, for example, you want 100 DSP processors to be brought out to the market. You want 100 DSP processors. What is the cost of each FPGA kit? 25K. 25K. Okay, and you will do some programming to that, some resources. You will allocate some resources, so the cost of those resources could be around 15K. So totally it is 40K per unit. But the thing is, at this cost, you are getting a laptop. At this 40K, you are getting a laptop which can do this task, which can do this task. So another disadvantage of FPGA is per unit cost is high. Per unit cost is high. Okay, but it is good for it is good for general purpose applications. And for if it is ASIC, what is the disadvantage? Time to market is quite high and low per unit cost. So what is the for example, you want to buy an i7 processor. What is the cost of i7 processor? It is something around 40K, something around 40K. But the same i7 processor you want to reproduce in FPGA. However, it is not possible in FPGA. But even though you want to do, its per unit cost could be multiple times higher than that. Okay. And as I told you, FPGA is quite larger than ASIC because it's a board which is half the size of your laptop or the computer or whatsoever. But in comparison to this, what about ASIC? ASICs are, they are chips which are hardly the size of your thumbnail. What is the size of your thumbnail? So that is the size of your ASIC chip nowadays, right? So, but despite this, where can we use FPGA? FPGA is used for prototyping. If at all you are not sure that whether your design works perfectly or not, you want to make sure that it will you want a prototype. So in such cases, in such prototyping, FPGA can be handy. And validating is quite easier with respect to FPGA. But here prototypes are quite costly because you cannot make one chip, right? If at all you are making chips, it can be in millions of numbers. It is difficult for I mean, it is not feasible to make a single chip or single prototype of a chip. Okay, so prototype must be accurately validating to avoid design iterations. And with respect to FPGA, it has lower barrier to enter to the competitors, because the moment you got thought in your mind, you can release it to the market with less time. But here, higher barrier to entry for competitors. For example, NVIDIA wants to bring a chip which can tackle Qualcomm. What is the time to market? 2 years. But within the span of 2 years, Qualcomm has already started working in the background and they released the chip within 1 year, 8 months. So that whatever the work NVIDIA has done in the past 2 years is gone in vain, right? Because no one is going to buy their product. So entry into the market barrier is quite high in case of ASIC. Okay. Do we have any doubts at this point of time? So now let us see what is ASIC flow. Okay. Let us see what is ASIC flow. ASIC flow generally starts with system specifications. Okay. System specifications followed by some architectural design, followed by architectural design. Once the architectural design is done, then we will do the functional architectural specifications and then the functional design. Then we will do something known as timing and relationship between functional units. Once you are done with this, then you need to write a code like logic design. You need to be doing like you need to use any one of the HDLs available. For example, whether it could be VHDL or Verilog. So you should be using any one of this language and you have to write your RTL code. Okay, you have to write your RTL code. Once the RTL code is written, then you have to generate something known as netlist. Netlist can be generated by a process known as synthesis. Okay, by a process known as synthesis. So netlist is generated. Once the netlist is generated, then there are some series of steps that are involved in a physical design. Some series of steps are involved. Once the physical design is done, then you will go to the layout stage. If everything is good in layout, then we do various checks like ERC, electric rule checks, and design rule checks, and layout versus schematic checks. There are a lot of checks involved, so we will do such checks, and then we will be sending our device to the fabrication unit. In the fabrication unit, I think you all know, like there are wide variety of steps included in fabrication, like etching, light photolithography, mm, and P-well process, N-well process, or twin tub process. All such process will be involved in case of a fabrication. So, can anyone name any few fabrication units across the world? Can anyone name few fabrication units across the world, famous ones? See, TSMC, Taiwan Semiconductor Manufacturing Unit. In fact, TSMC is the main reason why China is consistently claiming that Taiwan belongs to their mainland. Okay. and other famous manufacturing unit is Global Foundries. Okay, these two are the quite famous things that produce chips. Okay, and once the chip is ready, packaged, then the packaged chip is tested and they are released into the market. So this is a simple flow of ASIC design cycle. Now let us see the design flow of FPGA. Just give me a moment. Yeah. So what are the applications of ASIC? So based on our discussion so far, you can tell me like what are the applications of ASIC? Wherever you see a chip embedded into something, that is an ASIC. Wherever you see a chip embedded into something, that is ASIC. For example, our laptop. Our laptop has a lot of chips into it, so they are ASIC. Your tablet, phablet, whatever, it is a ASIC. Your mobile phone, that is an ASIC. Your washing machine, that is an ASIC. Wherever you see a chip included into it, that is an ASIC. For example, communications. Okay, so in your cellular phones, wireless routers or other devices, you can use this ASIC. And even in your consumer electronics like set-up boxes, your air filters like ACs, and all such consumer electronics will also be having ASICs into this. And our industrial controllers like automated robots, so those things will also be having ASICs into them. And automotives is in fact, if you see today's world, it is running towards EV, and a small EV vehicle would typically be having 400 to 600 microprocessors into it. Can you imagine how much technology is getting embedded into EV? So lot of technology is getting a small scaled version of a EV vehicle will be having at least 400 to 600, a minimum of 400 to 600 microprocessors into it. Okay, so even our automotive industry is using ASIC. Okay, so you see, our car is quite small. In that, can you imagine placing 400 to 600 FPGAs into it? Is that feasible? Size of an FPGA is half the size of your laptop. So can you imagine placing such 400 to 600 FPGAs into your car? Is that a feasible thing? No, it is definitely not feasible, right? So both the things have their own advantages as well as disadvantages. Okay. So that's about automotives. And even in cryptocurrency mining also we will be using ASIC, and as well as in medical devices. For example, artificial pacemaker. See here, artificial pacemaker. And even in imaging, for example, let us assume this is your heart. In some people, older people, what happens is their heart will not beat properly. So for that purpose, there is a pacemaker. Actually, a natural pacemaker is there on the top of their heart, which will provide impulse of currents, to the heart, so that heart beats. But whenever due to some reasons your heart beating drops, maybe a healthy heart should beat 72 times a minute, right? So if it is beating at a slower rate, maybe around 40 to 45 times a minute, it means that there is something wrong in that particular patient. So what doctors will do is they will install an artificial pacemaker like Sandvac or something artificial pacemaker. What it will do is it will keep on detecting the movement of the heart. Once the heart rate falls below a threshold, what it will do is it will send a small current shot, small impulse of the current. It is like you are giving an external current shock to your heart. It is quite low one. Okay, so you will give impulse of current to your heart so that it starts beating again. So that is how our even the ASICs are used into our medical devices. Okay. So now so far we have seen flow cycle of ASIC. Now let us see the flow cycle of FPGA. You can clearly see the differences between the flow cycles of all these things. Okay. So what is important thing in FPGA? The important thing in FPGA is generating the bit stream. Okay, bit stream generation is the important thing. Okay, once you are generated the bit stream, you can simply dump this bit stream into your FPGA. Then your FPGA will start working as per your intention. Okay, so here the flow is almost same until logic synthesis and RTL. Okay, until RTL coding, the flow is same. The change starts right from the synthesis. Okay, once you are done with synthesis, then you have to generate the netlist. After netlist, what you have to do is you have to do something known as mapping. Okay, so you have to do something known as mapping. What is mapping? I will tell you what is mapping. Maybe in due course of time. Okay, once mapping is done, then what you will do is you will do something known as placing and routing. Okay, but here the thing is, once the netlist is completed, once the mapping is completed, once placing or routing is completed, at each and every step, what you have to do is we have to undergo logic or timing simulations. At each and every step, once each and every step is completed, we have to do timing simulations. We have to do timing simulations in case of FPGA. Once placing and routing is done, then we will be generating a bit stream. Then what we will do is we will be generating a bit stream. Generating a bit stream is nothing but it is ones and zeros. This bit stream is dumped into the FPGA. Once it is dumped, then your FPGA will start working as a chip. I would say it has the functionality of a chip, but as per the size wise, it is 100 times bigger than the ASIC, I would say. Okay. So let me just show you one. Yeah. Yes. So this is spec of Nexus A7. Okay, Nexus A7. Basically, this is how your FPGA looks like. Okay, this is Nexus A7 FPGA. It has lot of things embedded into it. It has JTAG, it has a USB port, it has a Ethernet port, it has some connections into it, it has LEDs, it has a 7-segment display. For example, here you see it has some 7-segment display, and here you see all these tiny things you are seeing. No, these are all LEDs. These are all LEDs that will glow. And here whatever the things that you are seeing here, no, these are the switches. These are the switches which you can toggle. Tick 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 tick, you can do that toggling by using these switches. Actually, all these switches is associated with a number. Maybe it is difficult for you to see here, but they are all associated with a number on them. So this number we need to map by using something known as XDC. XDC nothing but Xilinx design constraints file. A XDC constraint file is there, by using which you have to do the mapping. For example, let us assume that you want to use this Nexus A7 board as an AND gate. Okay, then for AND gate, how many inputs are required? Two inputs are required. How many outputs are required? One output is required. One output is required. So it means that you should use two of these pins as input pins. By the way, you can use any two pins. Here we have multiple pins like 1, 2, so on. We have, I think, around 15 pins we have. So among these 15 pins, which pin you want to use? Maybe, for example, I want to use this pin and this pin. So you need to map these two pins accordingly. Okay, you need to map these two pins as per your requirement by using a file known as .xdc file. XDC stands for Xilinx design constraints file. There, where you're telling the tool, you're providing some constraints to that in such a way that I want to use only these two switches as part of my input, and I want to use this switch as part of my output, or something of that kind. You should tell to the tool. Okay. By the way, uh, Xilinx is the Xilinx Vivado is the one which we will be using in order to program our FPGA. Okay. In case of here, it is Nexus A7 board. Okay. Fine. Let me go back to the PPT. So that is what we will be doing in mapping. In mapping, what we will do, for example, you want a 10 input AND gate. So what you need to do, you need to map 10 pins as inputs and one pin as output or whatsoever. Okay. By using one particular file, that is XDC file. XDC stands for Xilinx design constraints file. Okay. So now you tell me, what are the applications of FPGAs? So far we have seen applications of ASIC. Wherever you see a microprocessor getting embedded, that becomes the application of a ASIC. Now what are the applications of FPGAs? Okay. First application is, okay, see here. First application is designing ASICs using FPGA. You are not sure whether your ASIC will work properly or not. So initially what you will do, you will design your ASIC using FPGA. and case studies in the energy industry. See, for example, there is an industry, a small scale industry is there, okay, whose turnover is typically 100 crores 100 crores a year, whose turnover is 100 crores a year. They want to do some analysis. For that purpose, they need a chip. If at all they want a chip that, which is not available in the market, what they have to do? They have to manufacture the chip. They have to manufacture the chip. They have to manufacture the chip means they have to go to any one vendor or manufacturer like Intel or AMD or Nvidia. They have to go to someone and tell their requirement so that a chip will be given to them. But the thing is, it involves millions of US dollars. It involves millions of USDs. But their company turnover is only 100 crores. How can they afford it? Quite not possible, right? So that is where FPGA comes handy. Okay, they will buy FPGA with simply 25,000, and they will do whatever they will do the necessary programming to it, like whatever the programming they want to do, they will do. They'll spend about 2 months to it. Okay, they will do and they will readily use it. Okay, it is done within 1 lakh rupees. Where is millions of USD and where is 1 lakh? Okay, that is where the FPGA comes handy. So it is used in case of for case studies in energy industries. And also, if at all you want to do any kind of improvements in your automotive experiences, there also you can use your our FPGAs. And most of the real-time systems will be supporting our FPGAs. And our aerospace and defense, many of the aerospace and defense things will be using FPGAs. And even this FPGA can be used in communications and all the SDN networks. And you might be knowing about CV, the computer vision. So many of the computer vision systems nowadays are using FPGAs. Okay. So this is about applications of ASIC and FPGA. Okay, so now let us see the architecture of FPGA. This is how basically an FPGA looks like. Once have a look at this, and how many different things can you notice here? How many different blocks can you notice here? Yes, how many different blocks can you notice here? One is CLB, one is SB, one is CB, right? So CLB stands for configurable logic block. Okay, CLB stands for configurable logic block, and SB stands for, just give me a moment, let me grab a pen. Yeah, SB stands for switch box. CLB stands for configurable logic block. And what about CB? CB stands for connection box. So if you see, it has some horizontal routing channels as well as vertical routing channels. It is vertical routing channels and it also has horizontal routing channels. It has CLBs. See the what is CLB stands for configurable logic block. Means it is a logic block. It is a logic block which can be what? Which can be what? Which can be configured. Which can be configured. With the moment I say configuration means what? Programming. The moment I say configuring, programming comes into the picture. Today, you program it, you configure it as an AND gate, that's fine. Tomorrow, you reconfigure it as XOR gate, that's fine. And day after tomorrow, you reconfigure it as a DSP processor, that's fine. Okay. So, what you have to do, there are many logic blocks available into our FPGA which can be configurable. Okay, you want to configure it, you can configure it. For example, you feel like a single logic block is not enough, then you can take the help of the another logic block. Then you can take help of another logic block which can be connected by using your switch box as well as the connection box. Okay, so what is FPGA? FPGA will be having more than two configurable logic blocks. If at all it is having more than two CLBs, then it is called an FPGA. If it is having two CLBs, those two CLBs should communicate with each other. They cannot communicate directly. So we need a connection box as well as a switch box, which can ensure the seamless communication between different CLBs. Okay. Any doubts so far? Okay. Can FPGAs replace ASICs in critical applications like medical devices or aerospace? Yes, already FPGAs. See, uh, these can be prototypes, yeah. Okay, I don't know who asked Gautam or someone. Okay, so FPGAs currently, for example, let us assume you want to manufacture a robot which can do liver transplantation. For example, let us assume you want to invent a robot which can do liver transplantation. Okay, liver transplantation. For this liver transplantation, what you are doing is you are inventing a robot. So you are the one who is designing it. So if at all you want a chip for it, if at all you want to chip, you want a chip. You currently you are in R&D stage. You are not sure whether your robot will work properly or not. So can you directly go and manufacture a chip? Give it for manufacturing? No. So for that purpose, what you will do initially you will do this on FPGA. Initially, you will do this on FPGA, and you will do lot of experimentations. Okay, you will do lot of experimentations on animals or whatsoever the things available to you. If the liver transplantation is successful with those things, and you feel like my FPGA is working fine, then with the configurations that you have in your FPGA, you can go back to any vendor and give these configurations. They will manufacture a chip and give it to you. So yes, it is being used in medical devices. Okay. Next. How can we do practically? Yeah, see, we are going to discuss that how we can do this practically. Okay, can you explain what is the use of mapping? See, that's what I told you. No, you have. Okay, see here, there are lot of switches here, right? We have many switches here. You need to map these switches. Like for example, you want to make sure that your FPGA is working as a 2-input or 3-input AND gate. Okay, 3-input AND gate. There are many inputs available to you. 16 inputs are available to you. Which input you want to use? Yeah, whether this one or this one, or you want to use this one and this one. Which one you want to use? You need to map them. Your Vivado tool won't do it automatically, right? It is you who has to map, like which one should be used as an input, which one should be used as output, or what is that properly. Okay, so you need to take care of that. So that is the practical use of mapping. Okay. So again, what is the main difference between ASIC and that's what we are discussing so far, right? Wherever you see ASIC, time to market for an ASIC is quite high. Okay, and if it is FPGA, it's quite low. FPGA can be done, brought off the shelf, and you can reconfigure it, whereas an ASIC reconfiguration is not possible. Okay, anyone? You provide RAR, what are you asking, man? Participation certificate and all, it's okay. Okay, so this is how the typical architecture of FPGA looks like. So let us deep dive more into architecture of FPGA. So let us see what does this CLB has in it. Configurable logic block, what does it have in it? Okay, as I told you, the FPGA has an advantage of reprogrammability. Okay, it has an advantage of reprogrammable hardware architecture, right? So the architecture supports reprogrammability. FPGA basically consists of what? It consists of CLBs, configurable logic blocks. All the things that you are seeing here, these are all what? They are the CLBs. And also you will be having some input output IO blocks. Okay, whatever the things that are there here, they are all input output IO blocks, and you will be having connection box as well as switch box or switch matrix connections. Okay, in FPGA, what is quite important in FPGA is CLB, configurable logic block. So in FPGA, each CLB consists of what? It consists of 2 slices. Each FPGA consists of 2 slices. These slices are further divided into 2 logic elements. Okay, it means that totally there are how many logic elements? Totally there are 4 logic elements. Let me repeat. In FPGA, what is quite important is the CLB. So CLB will be having 2 slices. Each CLB will be having 2 slices. This is slice 1, slice 2. Again, each slice is further subdivided into 2 logic elements. This is logic element 1, this is logic element 2. In that case, this is logic element 3, this is logic element 4. It is something like that. Okay, again, I said this is logic element 1. What does this logic element consist? The general question, right? What does this logic element contain? It contains a 4-input lookup table, a multiplexer, a D flip-flop. Okay, basically, I said like what is important in FPGA? A CLB. What is there in CLB? CLB will be having as I told you, two slices. In each slice, there will be two logic elements. So what is it means that CLB is consisting of logic elements, right? CLB is consisting of logic elements. What is there in logic element? Logic element will be having a 4-input LUT, that is the lookup table, and one multiplexer and one D flip-flop. Okay, so now let me summarize. What is important in FPGA? CLB. What does a CLB have? CLB have a logic element. What does a logic element have? Again, the logic element is having LUTs in it, 4-input LUT, and a multiplexer and a D flip-flop. So here the general question arises is, what is an LUT? What is a lookup table? We will see that. Okay, we will see that. Okay. See, this is how generally the CLB looks like. This is how generally CLB looks like. Maybe it is difficult for you to digest, but this is the slice 0. Okay, this is slice 1. This is slice 2. This is slice 3. There are some slices. Okay, and each slice is again having, as I told you just before, logic element into it. Each logic element is having 4-input LUT, a multiplexer, and a flip-flop. Okay. So this is how a logic element looks. Okay, this is how logic element looks. What it has, as I told you, it has a 4-input LUT. It has a 4-input LUT. Okay, and it has a multiplexer. It has a flip-flop. So basically, your FPGA is consisting of what? If someone comes and asks you suddenly, what FPGA consists of? What is your answer? Your answer should be simply in 3 words. It consists of a 4-input LUT, multiple 4-input LUTs, multiple flip-flops, multiple multiplexers. That's it. That's the simplest answer. Okay. What does an FPGA consist of? FPGA consists of multiple number of 4-input LUTs, D flip-flops, and multiplexers. Okay. This is what we have seen. We are seeing is a single slice of a CLB. Okay, as I told you, what is a building block of FPGA? This is CLB. What does CLB consist of? CLB consists of logic blocks. What does a logic block again consist of? It consists of LUTs, flip-flops, and multiplexers. Okay, fine. So, for example, what is lookup table? Here LUT is there. What is this lookup table? The general question comes like, what is a lookup table? We will see. We will see what is a lookup table. Okay, let me explain about the lookup table a little bit here. Okay, because I have some space over here. So what is a LUT? For example, let us assume that you want to make sure that your FPGA works as an XOR gate. So what is the behavior of an XOR gate? Okay, 0 0 0 1 1 0 1 1. These are the inputs. What is the output corresponding to this? 0 1 1 0. Okay, so what are this? This is A1, this is A0. So what is this? This is a 2-input LUT. What is this? This is a 2-input LUT where it will have all the possible combinations for your inputs. What are how many number of possible combinations for 2 inputs? 2 power 2, 4 inputs. If at all you have 5 inputs, how many number of possible combinations? 2 power 5 equals to 32 number of possible combinations, right? 32 number of possible inputs. So the moment I say 5 input LUT, it means that how many number of different addresses it has? It will be having 32 different addresses. The moment I say 2 input LUT, how many different addresses it has? It has 4 different addresses. What are they? 0 0 0 1 1 0 1 1. Okay, so what is this? This is a address line. What is this? This is a data path. I could call this as address path, and I'll be calling the output as what? Data path. I would be calling output as what? As simply data path. Okay, so here our address lines will be inputs. Okay, and data line is output. Clear? Our data line is the output. From the discussion I had so far, I could conclude that address line is the input and data line is the output. So what can you do in data path? Can you write into data path? No, you can only read. because lookup table is already created. Okay. By the way, it is we who is designing this LUT. See, CLB stands for what? CLB stands for what? Configurable logic block. So it is you who has to configure your LUT. Okay, it is you who has to configure your LUT in such a way that A1, A0 are two inputs with these possible combination of inputs like 0, 0, 0, 1, 1, 0, 1, 1, which is having these possible combination of outputs. Okay, these are the possible combination of outputs. Okay, so this is what is the actual meaning of configuration. It is you who has to configure your LUT. Like I said, we have 4 input LUTs. We have 4 input LUTs. 4 input LUTs means how many different addresses you can give. 2 power 4 equals to 16 different addresses you can give. It means that you can configure your LUT for 16 different addresses. Okay, something like this: A3, A2, A1, A0, which will be having some 16 different addresses. So it is you who is configuring. It is you who is configuring, like what is the input, for that input what is the corresponding output. So it is you who is configuring your LUT. That is the actual meaning of configuring. Okay. It is the truth table that is written during the configuration. Okay. So this is the write operation. So whatever you are doing through the data path, okay, that is the output, that is the read mode, I would say. Okay, so uh, LUT is nothing but it is a kind of memory. Okay, LUT is nothing but what? It is a kind of a memory. It is a kind of memory. See here, I'm storing for 0, 0, I'm storing 0 as the output. For 0, 1, I'm storing 1 as the output. For 1, 0, I'm storing 1 as the output. For 1, 1, I'm storing 0 as the output. So it is a kind of what? A memory. So a general question should arise to you all. For example, here I have 4 input LUT. Means I have 4 inputs. Okay, but what if I want 5 input? It is not guaranteed, right? Like we always have 4 inputs only. For example, I want 5 inputs. For example, I want 5 inputs. Then what can I do? Then what can I do? So by or for example, I want to have 32 different locations. By using 4 input LUT, I can have maximum of 16 different addresses, but I want to have 32 different addresses. 32 different addresses is nothing but I want to have 5 input LUT. But in the FPGA, what I have is only the 4 input LUT. In that case, what I have to do? Can anyone respond? What I have is a 4 input LUT, but my application demands 5 input LUT, or my application wants to have 32 different addresses. In that case, what I have to do? In that case, what you have to do is you have to combine 2 different 4 input LUTs together by using your connection box and switch box. Okay. For example, see here. Here you have one LUT, okay, and which can give you 16 different addresses, right? Here I have one more LUT. Here I have one more LUT which can give me 16 different addresses. So if I combine these two things together, then what I can form is a 5 input LUT. How it can be formed? Simply take one mux, okay, take one mux and you just connect it to them. You just connect it to them and you give one control signal to them like E. So whenever E equals to 0, so you will be dealing with these 16 inputs. Whenever E equal to 1, you will be dealing with these 16 inputs. So totally you are getting 32, right? So if at all you want 5 input LUT, what you have to do? You have to combine 2 4 input LUTs together. Similarly, if at all you want 64 input LUT, 64 input LUT, what you have to do? You have to combine 2 32 input LUTs. Okay, getting? So this is how the configuration goes. This is the actual meaning of configuration. Here you are going to the core level or to the very ground level and you're telling like how should your LUT look like? Okay, what should the operation do? Okay, for 0 0, what should be the output? You are the one who is programming it. Okay, you are the one who is telling the tool that you should give this output for this particular input. Okay, so that is how it looks. Okay. So let us quickly look at the doubts of you people if you have any. Let me just quickly go to the chat box or okay. Oh, 18. I cannot answer all your doubts in single thing. Verilog or VHDL. Verilog is better, but VHDL is used in defense applications. What is VHDL? in VLSI design. Yeah, VHDL is a programming language. Okay, VHDL is a programming language. And can you explain which is better, Verilog or VHDL? Same doubt you're asking multiple times. Oh my God, Verilog is better in my way. CLB, DB, SB. What is this? CLB, DB. CLB is a configurable logic block. SB is a switch box. Is lookup table similar to truth table? Yes, obviously it is. Okay. And CLB consists of LUT mux D flip flop. Yes, it is correct. Lookup table. Same buses are used for data and address? No, different buses. Obviously, right? Here we do not have buses. We have pins here. In FPGA we have pins. Okay. How do use a LUT uh, for chip design in FPGA? I did not get your question. How does the size and configuration of LUT in FPGA impact logic synthesis? How does the size? See, you are least bothered about the size. Okay, here after synthesis, okay, we will discuss this. We will come back to this question a little later. Okay. So now you see here, these are the different uh, devices we have. Okay, different FPGA devices we have, like XCV50E, XCV100E to XCV3200E. Okay, each one will be having gate something around, as per the thing given here, 71,693, and the highest version of it would be having something around 4 lakh gates into this. Okay, and see this. For example, if you see the 50E version of it, the CLB array, or 100E, if you see 100E, if you see, it has 32,400 logic gates. And how many? I told what is the building block of FPGA? It is a CLB. So there are 20 by 30 CLBs. 20 cross 30 means totally there are 600 configurable logic blocks in case of XCV100E. Okay, 600 logic blocks. How many logic cells? How many logic cells? See, each CLB will be divided into what? Two slices, slice 1 and slice 2. Again, each slice is having two logic blocks into them. It means that totally there are four logic blocks. So 600 into 4 is how much? 2400. So approximately each logic cell will, each one will be having 2400 logic blocks. But here it is mentioned as 2700. Maybe they have considered it as 4.5. It is actually depends upon the vendor, or it varies from vendor to vendor. Okay, but basically this is a general calculation. Like if you have 20 by 30 CLBs, it means that you have 600 CLBs. Each CLB is further subdivided into 4 logic cells. So totally there are around 2400 logic cells. Totally there are 2400 logic cells approximately. So that is how the thing goes. Okay. Fine. Now, okay. So, yeah. So what is the application of this 4-input LUT? 4-input LUT is used to implement any one of the functionality, like combinational logic design. Maybe by combinational logic design, what do I mean? Maybe you want to implement something like a full adder, something like a full adder. You want to bring a chip. You want to design a chip which can work as a full adder. Okay, then you can do that, and it can even work as a distributed ROM, or it can even work as a shift register. Okay. And see here, not just the CLBs, there are various other dedicated circuits present inside the FPGA which has dedicated functionalities, like clock manager, multiplier, and RAM, and many other things. So what is the purpose of clock manager is to take care of the clock, whether you want any phase shift, whether you want to do some kind of deskew, whether you want to do clock division, all such things taken care by the clock manager. And multiplier block, it is having 18 by 18 multiplier. Okay, it is having 18 by 18 multiplier with signed and unsigned operations, which can give you the flexibility to deal with both the things. And RAM is a dedicated memory. It is about 16 KB. So what does an FPGA consist of? As of now, we know FPGA consists of CLB. Apart from CLB, what it has? It has a block, clock manager, and it has a multiplier block, and it has a RAM. Apart from this, what it will have? It will have Ethernet port. Okay, it will have JTAG port. Okay, it will have USB port. It will have many things into it. Okay. So see here, after synthesis your code looks, what is synthesis, by the way? What is synthesis? Synthesis is nothing but converting the given logic into equivalent gate level netlist, or converting the given logic into equivalent hardware. What is synthesis means? Synthesis is nothing but converting the given logic. I have written some logic, some code I have written here. This code is being converted into equivalent gate level netlist, or I would say it is getting converted into hardware. So this is what I would be calling as synthesis. Again, let me repeat, what is synthesis? Synthesis is nothing but converting the given logic into its equivalent gate level netlist, or I would say converting it into hardware. So see here, the beauty of synthesis is, can you touch the code? Can you touch the code? You have written some code into your laptop. Can you touch into the tool? Can you touch it? Is code a tangible entity? No, code is intangible entity. But the moment you do synthesis, what happens is it is generated into some form of hardware. Means something intangible is becoming tangible. Means your code which is intangible is getting converted into some form of hardware which can be fabricated and brought out into the real world as a chip. It means that something intangible is getting converted into tangible format like a chip. That's all possible because of what? Synthesis. Okay. What is synthesis? Synthesis is nothing but in raw statements. If you ask me, synthesis is nothing but converting the given logic into hardware. So something like this. For example, what is this code here? Can you all see this code and let me know what is this code for? It is a adder come subtractor. When mode is 0, I am performing a minus b. When mode is 1, I am performing a plus b. So it is an adder come subtractor. So after, so this is a what? This is code which is intangible. I cannot touch this physically, but after synthesis what happens? It is converted into some form of hardware like this. Some form of hardware like this. Once I give it to fabrication unit, what fabrication will unit will do? They will print a chip out of it and they will give a physical chip to me, which is tangible thing. Means something intangible is becoming tangible because of what? Synthesis. Okay. So we have to do the synthesis. And see here, once synthesis is done, we have to do functional simulation, timing simulation, and also even after the functional simulation we have to do post synthesis simulation, we have to do timing simulation, we have to do. If you see here, uh, let me just, yeah, see here in this FPGA flow cycle, see here, once netlist is generated, means once synthesis is done, what you have to do? You have to do simulation. Once mapping is done, what you have to do? You have to do simulation. Once placing and routing is done, what you have to do? You have to do simulation. Means logic or timing simulation, how many times you have to do? You have to do it many times here. Okay, every time you do some change, you have to undergo simulation, simulation, simulation. Okay. So see here. Once synthesis is done, what you have to do? Just give me a moment. Yeah. You have to do functional simulation. Once circuit is synthesized, what you have to do? You have to do post synthesis simulation. Once it is implemented, what you have to do? You have to do timing simulation. So this is the place where lot of STA concepts will be coming into the picture. STA stands for static timing analysis. Means like what is setup time, what is hold time, okay, what is clock jitter, what is clock jitter, and what is clock skew, oh, what is slack, what is slack analysis, what is positive slack, what is negative slack, how slack affects our design. So all such multiple things which are belonging to STA, that is static timing analysis, will be coming into the picture at this level of timing simulation. So don't worry, like maybe you know like what is setup time, what is hold time. So I'll be discussing little on what is clock jitter and clock skew. Okay. So let me go to the new slide. Yeah. So see here, if we go back, here netlist is there, mapping is done. After mapping, what you have to do? After mapping, what we have to do? We have to do placing and routing, right? So let us see what is placing and routing. So placing and routing is quite simple here. Okay. See, placing and routing is also known as PNR. Placement and routing are P&R. It's just so here what you will be doing is, for example, let us assume this is your home. Okay, this is your home, and here you want to have a master bedroom. Here you want to have a children bedroom. Here you want to have a drawing room. Here you want to have kitchen. Here you want to have bathroom. Something like this. So what you are doing, you are placing the rooms accordingly, right? For example, let us assume that this is your main door, and in front of the main door you had a bathroom here. Does that looks good? It looks very bad, right? So this is a bad design. So what you have to do, you have to remove it from here, and you have to keep it in some appropriate place. So what you are doing here, you are placing it properly. You are placing it properly. Similarly, in our electronic design also, for example, let us assume that this is our chip boundary, and this is the clock, and this assume that this is the module 1. Okay, this is one module, module 1, module 2, module 3, module 4, module 5, module 6, module 7 is here, and module 7 is the one which is using clock many number of times. Okay, which is using clock many number of times, and the clock to this is going like this. Okay, it is going like this. It is going like this. You may be asking, like, why can't it be straightforward route? Okay, it cannot be because there are multiple layers, hundreds of layers within a chip. So the route to a single module cannot be in a straightforward manner. So as a result of this, what happens? Your clock or the electron has to flow through this tiny channel. As the electron flows, there exists one more channel on the top of it, right? So whenever electron flows in two channels simultaneously, what happens? A capacitance will be forming. If the capacitance forms, capacitance effect will be coming to the picture. As a result, what happens? Heat increases. If the heat increases, what happens? Power consumption increases. If the power consumption increases, what happens? Your battery will be drained fastly. That is the reason you should not buy Chinese mobiles. Okay, your battery will be draining too quickly. So means just because of a channel having huge length, what is happening? Capacitance is coming into the picture. Because of that capacitance, what is happening? Heat is increasing. Because of that heat, what is happening? Power consumption is increasing. Because of that, what is happening? Battery is getting drained too quickly. So what is the solution for this? Solution is quite simple. Analyze all such modules which are requiring such a path, and you just place that module here, and you connect the clock like this. So this is what placing and routing. So you need to identify all such blocks and place them accordingly and route them accordingly. Okay, this is about simple idea or analogy about placement and routing. Here it is simply like, it involves deciding where to place, where should we place all our electronic components or circuitry within the limited amount of space. This is what about placing and routing. Okay. And okay, so let us go back to the next slide. So this is how, cells are placed and they are routed. So they are placed in appropriate places, like, like something like this. It is placed in the places something like this. Once they are placed, they need to be routed accordingly, right? You can see they are getting routed, right? They are getting connected, something like this. So this is about what? Placement and routing. Once the placement and routing is done, what we have to do is we have to generate a bit stream. Okay, we have to generate bit stream. Bit stream generation is the crucial step in case of FPGA designing. Okay, in case of FPGA. So this bit stream is generated in form of ones and zeros, and extension to this is dot bit. Okay, dot bit file will be generated by using the Xilinx Vivido tool. So it basically, this bit stream generation, it is a file which is containing binary data. Okay, so what does this binary data has? This binary data is typically having all the configuration information that we have given so far. Like, we have designed like 4 input LUTs, 5 input LUTs, 6 input LUTs. We have done lot of configuration with respect to LUTs. So all such configuration information is stored in form of the binary data. Okay, not only that, it also have the commands. Your bitstream, your dot bit file also has the commands that are needed to control the functionality of the chip, that are needed to control the functionality of the chip. Okay, and all of this information is arranged in form of what? Frames. this is arranged in form of the, for example, this is frame 1, frame 2, frame 3, frame 4, frame 5, frame 6, something like this. So this is arranged in form of frames. So which makes up the fundamental block for the FPGA configuration memory space. Once the bit stream is generated, so what happens after this? The bit stream file is generated. Uh, Basically, this is generated after elaboration process. Okay. Once the bit stream is generated, what we have to do is we just need to dump this bit stream into the FPGA. Once the dumping is successful, then your FPGA will be acting as the desired application. For example, you want it to work as an AND gate. So for example, you want it to work as an AND gate, then you will be configuring your LUTs as per the AND gate requirement. Then this LUT configuration, whatever you have done, that is converted into bit stream. That bit stream is dumped into the FPGA. Now your FPGA is working as a chip, which can simulate the behavior of what? AND gate. Okay, which can simulate the behavior of a AND gate. Fine. So what are the different FPGA families we have? Like, Altera, Spartan, Vertex, Artix. What we have seen the board just before in the spec is Artix 7. Okay, so this is how the boards look like. Artix 7, Edge, Spartan 6, Altera. So they have lot of things embedded onto them. Microcontrollers, 7-segment displays, LEDs. Okay, heatsink, JTAG port, USB port. Okay, a lot of things it has onto them. So this is a typical Arctic 7 FPGA board. Okay, uh, it has like it has high performance per watt fabric. Okay, means per watt of energy it can give you very huge performance, and it is typically used in DSP processings and AMS integrations. Okay, so all these things you might not be able to capture. So that's about the Arctic 7 board. So okay, so let us see what is clock jitter and clock skew. Okay, what is clock jitter and clock skew? So that assume that this is a D flip flop 1, this is D flip flop 2. Okay, assume that the clock is reaching here at 1 nanosecond. Clock is reaching at this point at 1 nanosecond. So what is our general expectation? Even here the clock will be reaching at 1 nanosecond, right? Even to this second flop, the clock is reaching at 1 nanosecond. But if you see the length, what is the length of the channel? Length of the channel is quite huge. Due to that, what happened? The clock is reaching at a later point of time, like 1.000001 nanoseconds. It is reaching. So it means that ideally the clock is not reaching both these flops at the same time. Okay, that is known as skew. So if I have to define skew, how can you define? Generally, see here the clock arrived at 1 nanosecond, but here the clock arrived at 1.00001 nanoseconds. It means that there is a difference in the arrival time of the clock. Yes or no? There is a difference in the arrival time of the clock. That is known as skew. Simply, there is a difference in the arrival time of the clock. That is known as skew. See here it is coming at 1 nanosecond, but here it is coming at 1.0001 nanoseconds. So there is a difference between arrival time of the clock. Here clock is arriving at 1 nanosecond, but here it is arriving at different time. So there is a difference between what? Between the arrival times of the clock. That is clock skew. So if I ask you to define clock skew, how will you define? The simplest definition possible is the difference between arrival times of the clock at different devices is called clock skew. Okay, are you able to understand? I hope it made sense on what is clock skew. Okay, now let us see what is clock jitter. What is clock jitter? So what is clock jitter? Okay, let me explain you one thing. See, assume that this is the clock. Okay, this is the clock. Okay, this is the clock. Okay, this is 0, this is 5, this is 10, this is 15, this is 20, 25, 30, so on. Okay. So what is our general expectation? Every time the falling edge will be happening at 5 nanoseconds, 15 nanoseconds, 25 nanoseconds, something like that. But in reality, it is not like that. So in reality, it is something like this. Actually, it is supposed to occur at 5 nanoseconds. But what happens is, it might be occurring at 4.99999 nanoseconds, or it might be occurring at 5.00001 nanoseconds. So in reality, it might be occurring at a later point of time. So it means that what is happening? There is a deviation in the clock edge, right? Clock edge is supposed to happen at 5 nanoseconds. But what is happening? It is not happening exactly at 5 nanoseconds. It is happening a little time earlier or little time later. So what is there? The clock edge is supposed to occur at 5 nanoseconds, but it is not happening at that time. There is some small deviation in its time. So that is known as what? That is known as clock jitter. Okay. See here, from one clock cycle to the next clock cycle, period is not exactly the same each time. Here, let us assume if we take from here to here, it can be what? 9.999 nanoseconds. But from here to here, if I take, it could be something around 10.000001 nanoseconds. Okay, so this difference is generally known as jitter. Okay, understood? This is about clock jitter. So that's about clock skew and clock jitter. Basically, these things will play a crucial role in case of STA, that is the static timing analysis. Okay, so this is how we will be programming our FPGA. Give me a moment. Yeah. So yeah, that's about it. That's it. If you have any doubts, I'm open to doubts. So you can ask me if you have any doubts. I'm open to doubts now. Internships, yeah. If you want internships, basically we at HAW will provide you practical internships. You can contact our administration for that. Maybe Bhavya can take care of this. If at all you are interested in internships, or if at all your expectation is with respect to the paid internships, you see, Intel frequently takes interns. Okay, and typically they are paid around 45 to 50K per intern per month. So you search in LinkedIn, like where are the jobs getting posted. So that's how you can get into some product based company as an intern. Okay, basically LinkedIn, you should be quite active. Okay, you want this recording class, probably you should ask the how does the size. Okay, so any doubts you
This
have?
recording will be available on YouTube, Prithvi, so they can visit
Okay.
our YouTube handle and then look at the same class.
Okay, so if you have any doubts, please share. I am open to doubts. And let me tell you just one thing. Okay, let me just come out of the presentation mode, and let me just take a few moments to explain, like, what is the potential currently VLSI industry is holding in India. Okay, just give me some quick moments. Okay. Let me just keep it in presentation mode. Once read this here, go through the slide, read every line by line. So if you see here, uh, if you see here, as of 2024, the market hold of semiconductor industry is $0.72 trillion. But by 2029, it is almost going to get doubled. Like it is 1.21 trillion USD. 1.1 trillion USD. So it is getting almost doubled. So by 2024, you might have already seen there is a surge in demand for VLSI engineers. Now the demand is almost getting doubled. It means that the requirement for employees will also get doubled, right? A simple logic, right? And also Indian government has observed this trend, so that is the reason what they have done is they have started a flagship incentive program. As a part of this, what happened is they are starting three manufacturing units in India. Okay, two at Gujarat, one at northeast, probably in Assam. So and not just that, semiconductor industry in India is having quite a huge scope. Let me show you that in the upcoming slide. There is a requirement of at least 3 lakh semiconductor engineers in upcoming near future. You just read the bullet points that are highlighted. So see here, Indian government is investing a lot into semiconductor industry, and they have given incentives, and more than 76,000 crores have been poured into Indian semiconductor industry by government of India. And not just that, as per the government of India and as per the global report statistics, India alone, not the whole world, India alone is going to see a shortage of more than 3 lakh semiconductor engineers. Okay, more than 3 lakh semiconductor professionals. It means that those who ever attending this session and those who ever getting passed out by 2027, they have already assumed that you all got placed into semiconductor industry. You all are already got placed into semiconductor industry. Despite you all getting placed into semiconductor industry, there is still a shortage of more than 3 lakh semiconductor engineers. It means that VLSI is giving you a huge scope for your career, a huge scope for you to get settled into the VLSI industry. Because it is not me who is telling you to convince. Because you see the statistics. No, it's government of India who is telling that India alone, not the whole world, India alone requires more than 3 lakh engineers by 2027. It means that there is a huge void or huge space in which you can come, sit, and earn. And not just that, semiconductor industry will pay you huge. As I've told you just before, if at all you got placed into Intel as an intern, Intel will pay you 45K. Okay. If it is some other company like Nvidia, they will pay you 85K, depending upon how you perform and depending upon from which college you are. So semiconductor industry will pay you huge because the work that you're going to do is also quite enormous, quite difficult. Okay, and just read this: 250,000 to 3 lakh professionals across various verticals, including R&D, manufacturing, advanced packaging by 2027. India needs these many people. It's just India who needs. Think about the whole world. Okay, so there is a huge scope for you guys to come and fit into the semiconductor industry. So utilize this opportunity within the next 3 years and get placed, get settled well. We at HIEE will help you to get placed, to get the core skills that industry demands. Okay, so whatever the industry demands as per the industry is considered, so we at HIEE will help you to achieve all those things. Okay, so these are the things that industry expects you to become a proficient. This is how you can be industry ready. First of all, you should be strong in digital electronics. Once you have digital electronic basics of digital electronics cleared, then you should be having knowledge on Verilog, system Verilog, and UVM. Once you are done with that, then you should have some debugging skills. Once you're done with that debugging skills, then you should know some standard protocols like Quasta-SIM, Xilinx, Vivado, or something of this kind. Once you're done with that, you should have knowledge on PCIe. I myself have good expertise in PCIe. I have worked for Intel Penang for almost 3 years on PCIe. And also I have worked on Ethernet. Okay, I have worked for Star5, Chinese client. Okay, on Ethernet. and AMBA, AXA, AHB, APB, SPI, I2C, UART, all these are the protocols. So you need these knowledge. Okay. You also need some basic knowledge on scripting like Python, Tekil, or Perl. So this is how you can become industry ready. So all these things might seem weird to you. So maybe some of you might be hearing the word protocol for the first time. So don't worry, don't get panic. We at HIEE, especially me, will be helping you people to get placed to become industry ready. Okay. So as I told you, there is a huge scope for VLSI industry in upcoming future. Currently, it's already there. So it is about to become popular in India. So utilize this opportunity, get settled in your life quickly, and collaborate with us. We at HRW will help you to achieve your goals. Okay, that's all from my side. If you have any doubts, we can take those.
Yeah, guys, the session is open for doubts. If you are having any doubts, you can post your doubts in chat box.
What is this? What is this? Too many. Okay. Both are eligible. Okay. Where is the place for offline course? See, we offer both online and offline. I think we are situated at Amirpet for offline course. Okay. Oh, okay. Let me just maximize this. It's difficult for me. What are the topics to be prepared for entering into semiconductor industry? Like, what are the fundamentals be excelled? Yeah, you should be first thing is you should be thorough with digital electronics. Once you're done with digital electronics, what they expect from you is knowledge on Verilog coding. Once you're done with Verilog, it should be system Verilog and UVM. So these are the three things you should be familiar with, like Verilog, system Verilog, UVM. After that, any knowledge on protocol, like it could be APB, AHB, AXI, CHI, PCIe, USB, Ethernet, any one protocol. Okay, so let me repeat. Like you should be having knowledge on digital electronics, Verilog, system Verilog, UVM, and then any knowledge on protocol. Even APB is fine. Okay. Anything else? Or yeah, ask something productive, man. For everything, whether you are an electrical student or electronic students, it doesn't matter. The skill set remains the same. Okay. Yeah, we do start every batch once every 1 month. Yeah, so you can come. We do offer only DV courses as of now. We are not yet into PD and DFT. So very soon we will be going into PD as well. Clock skew and jitter are different. See, skew is nothing but difference in the arrival time. Okay. Skew is difference between the arrival time of the clock. But jitter is what the clock edge is getting deviated. Right? The edge of the clock is getting deviated. But skew is because of the propagation delay. Okay, propagation delay because one device is at 1 kilometer, second device is at 1,000 kilometers. So the propagation, your clock has to travel 1,000 kilometers and then reach the device too. So by the time what is happening, some nanoseconds of delay is happening. That is skew. And contrary to that, what is jitter? Jitter is deviation in the clock edge. Okay. Next, anything else from anyone? How much does it cost for training 3 years student? Maybe all this non-technical thing can be addressed by our staff. Okay, maybe they'll
Yeah,
get back to
sir,
you.
sorry to interrupt you. Regarding the training fees, regarding everything related to the training, you can contact us. The numbers will be posted in the chat box. So if any questions related to the session or any technical questions, you can ask.
My LinkedIn ID, you just Yeah, sorry. It seems like I'm disconnected. Where were we at the discussion? Bhavya, are we connected?
Yes, Prithvi, you're there. And there are questions from Gautam talking about how does the size and configuration of LUTs in FPGA impact logic synthesis?
Oh, just a minute. Let me see the question. Where is the question?
It's at 11:56.
Mm, Can you repeat the question for me?
How does the size and the configuration of LUTs in an
Mhm.
FPGA impact logic synthesis?
See, the size, by the size you mean to say 4 input LUT, 5 input LUT, 6 input LUT. So 4 input LUT is by default available. How about 5 input LUT? You can get this 5 input LUT by using two 4 input LUTs. If at all you want 6 input LUT, you can get that by using two 5 input LUTs. So depending upon that, the synthesis will be performed. If it is 4 input LUT, after synthesis, the hardware that you are going to get is quite small. But if it is 5 input LUT, after synthesis, the hardware you are going to get is obviously huge in comparison. If it is 10 input LUT, obviously it is quite huge in comparison with 4 input LUT. Okay.
Okay, there's a question from Hemant. Sir, does HAW have DV only or any other ports as well as PD and DFT?
We have already answered this, right?
Okay. Mm, sir, does these topics DLD very low or enough for any kind of training institute exams?
Any kind of training institutes? Training, why do training institute will keep entrance examination? Basically, see, maybe your question is like company's entrance examination, but DLD and Verilog are not enough. You should have some knowledge on system Verilog, UVM, and also on protocol. Okay. By the way, are we simultaneously on YouTube?
Yes, we are.
Oh, we are live on YouTube. Oh, I don't know that.
Okay. So we are live on YouTube, guys, and the respective recording will be available. We don't delete the live sessions at all. You can come back and review the session at any moment you wanted to. Guys, somebody asked about a certificate. Yes, guys, you will receive the certificate. Please look at your registered email ID that you have given here, and you will receive the certificate to that respective email ID. Please give your valuable feedback, guys, everybody. Okay, we are sharing the YouTube link as well on the chat box. You can look at.
Yeah, we do have classes online. Okay, so on.
Yeah, Manjunath, would you like to address the gathering for the
Yeah,
batch and all? Yeah.
I'll address regarding the batch and all. So while I'm looking into the chat and all, most of the students are asking for internship regarding the VLSI. So I want to announce you one thing that from tomorrow onwards, we are starting a new internship batch on VLSI. So whoever want to register for that, you can reach out us. The numbers will be given in the chat box. From tomorrow onwards, you will be having the batch on the VLSI. Then coming for the job orient, this internship will be most useful for the people who are in the second years and third years, and for the people who are pursuing fourth year and passed out students. For you people, we are having a job oriented course, which will be starting from May 22nd onwards. So this will be the 5 months training program where you
It
will
is 5
be
to 6 months.
it's 5 to 6 months, 5 months of the working days you will be having. So to be precise, I can say it's a 5 to 6 months of the 5 to 6 months of the course duration. So in this course duration, you will be you will be trained on digital Verilog. Then you will be trained on SV and UVM. You will also be having the protocol training. Then followed by you will be having the placement assistance also. In this program, you will also be having the hands-on experience on the protocols and all. So whoever interested to join this batch, for that also you can contact, and the registration links also posted in the chat box. From there also you can register. We'll reach out, and whoever are interested to join for internship or for the regular batch, you can also write something as interested in the what we say comment section in the feedback form. From there also you'll get contact you. And one more announcement that if you are having any friends from mechanical, electrical, or some civil departments also, so you can also help them out by saying that from 22nd onwards, we are also starting the new batches on electrical system designing, mechanical designing, and civil. In that also, if your friends are interested, you can give our numbers to your friends also. Okay. So for the VLSI internship and for VLSI regular job oriented batch, you can reach out. So can I get to know how many people are interested for VLSI internship, which is going to start from tomorrow? Can you quickly type in the chat box interested? Yeah, guys, I can see most of the people are interested for VLSI internship, which is starting from tomorrow onwards. See, the point is that we will be charging 5,000 for internship, okay? But one offer for all the people who are attending for this webinar. So now you will be filling the feedback form. Once you are filling the feedback form within some time or within 1 or 2 days, you will be getting the certificate to your registered mail ID. So whoever showing that certificate to our team members, you will be getting the 1,500 rupees of discount. Okay. So the people who are joining from outside without attending this webinar, they will be charged for 5,000 rupees. But whoever attending this webinar and whoever showing their certificate of this webinar, you will be getting 1,500 rupees of discount. And this offer will be valid for 2 days only. Okay. So tomorrow anyway the classes will be starting. So for the given numbers, you can immediately contact and you can register for the sessions. And this certificate offer will be valid for 2 days. Whoever showing the certificate, you will be getting 1,500 rupees of discount from that 5,000 rupees. So this will be the one offer which we are giving from the HIW to empower the engineers because we at HIW are mainly focused on empowering the engineers. In that manner, this is also one of the internship program where you'll be getting the immense knowledge and the same thing with your May 22nd course also. So for that also you can contact us.
Please fill your form, feedback form. You will receive it mostly by today, end of the day, if you have filled the form. You can contact our team in case you didn't receive your form. You can contact us by tomorrow and we will share your certificate by tomorrow in case you didn't receive it on your email ID. Kindly, we request all of you to please do check your spam folder also for the certificate before contacting HIW team. Thank you.
Yeah, we do have online internship also, yeah.
Yeah, online internship is also available, Sunita.
Okay, then, if that's the thing. Thanks, Bhavya and Manjunath, and thank you, rest of the folks.
Yes, sir. I take
Thanks.
immense pleasure to thank you. The session you have delivered is very wonderful, and many of the people got insightful message from your side. And we are looking for more collaboration with you. And I hope most of the people will turn out and will collaborate with you for the future insightful. Sir, thank you so much.
Yeah, thank you, man. Thanks, everyone.
Yeah, thank you.
See you soon. Bye.
Yeah. Thank you guys. Once again, I'll take my pleasure to thank everyone for attending this session. And I'm very much happy. We from HAW are very much happy to see you people. And we are very much enthusiastic for further collaborations with you people. And once again, I'm intimating you that from tomorrow onwards, the VLSI internship is going to start, which is 5,000 rupees of fees for individual. And if you're showing the certificate, you will be getting the course for 3,500. And from May 22nd onwards, we will be starting the job-oriented course on VLSI. So for whatever the course you are interested, feel free to contact our team. You can also contact us in Instagram. You can also contact us through our website also. Then if you are having any friends from ECE, mechanical and civil and electrical, for them also we are going to start the job oriented courses from May 22nd onwards. So you can also give our contact details for them. Yeah, for the rest of the informations regarding the fees and all, you can contact us on the given numbers, or you can text us on the given numbers. We'll get back to you. And if you are having any doubts also in the chat box, the feedback form is posted in the comment section. You can write. So whatever the doubts you will be having, we'll get back to you.